this video, the point of concurrency we're discussing is the incenter. Again, concurrent means where three or more lines intersect at a single point. And so a point of concurrency is that point where three or more lines intersect. And it is a big deal to have a point of concurrency when you have a certain kind of line drawn into a triangle. And so this time we're talking about the incenter. And so the definition, and there's different ways you could define incenter, but for now we're going to define it as the point of concurrency of the angle bisectors in a triangle. Okay, and so there's not a real good way to draw in the angle bisectors, but we'll just do our best to get them drawn in. And so if we, just kind of estimate here, looks like I'm cutting that angle in half or so, like that. And then I'm going to do my best to do it here too. And then do my best to do it here. And when you do that, if you draw in the angle bisectors correctly, then what you end up with is all three of the angle bisectors intersect at a single point, and we call that point the incenter. There's a theorem related to incenter. On our book, it's Theorem 5.7. It's called the Incenter theorem. And what the Incenter theorem says, the bisectors of the angles of a triangle intersect at a point equidistant from the sides of the triangle. Now, the key here for this one is this idea of equidistant from the sides. For you to measure the distance from a point to a side, you have to do it at a perpendicular. So what this theorem is saying is the intersection of the angle bisectors, which we now know from the definition above, is the incenter. If we find the incenter, then we know that if we measure the distance to the sides, it's going to be the same. And so if I draw in a distance, remember, distance from a point to a side is always at a right angle to the side. And so it looks something like that. And so, and then these three segments are all going to be the same. That's what the angle bisector or the incenter theorem is saying, is that those three segments that go from the point to the side of the triangle are going to be the same as long as that point is the incenter. Okay, now if you have three segments protruding from a single point, that means if they are all the same, that they're going to go through the same circle. And so that's also the case here. And so if we draw in a circle, we call that circle the inscribed circle because it's put inside a circle. And the incenter is also known as the center of the inscribed circle of a triangle. So the incenter is also the center of the inscribed angle, circle of a triangle. When you're inscribing a circle inside a triangle, make sure that you put the circle in a way that it touches all three sides. If it doesn't touch all three sides, then it's not an inscribed circle. Every triangle has an inscribed circle that you can create. So just a quick kind of let's look at this proof. You want to show that the bisector of the angles intersect at a point equidistant from the sides of a triangle. And so we need to show that these three lengths are the same, not just be given them. That's the other side, is the given part of the equation here. And so we need to show that these triangles are the same so that then we can show that the side lengths are the same. This is an angle bisector. And so that means this segment and this segment are going to be congruent to each other. We also know that these are right angles. And because those are right angles, they're going to be congruent as well, because right angles are congruent to each other. And then from there, we also know that, say we label these points, we know that AD is congruent to itself. And so by the reflexive property, then we would have these two triangles, AED and AFD, that are congruent to each other. And they're congruent to each other by side-side angle, or not side-side angle, by angle, side, right? We have the right angles congruent to each other. We have the other angle created by the angle bisector congruent to each other. And then we have the hypotenuse congruent to each other, because those are the side lengths. And so that allows us to prove this congruent by angle, side, which then shows us that ED and FD, the distance from the point to the sides, is going to be the same by CPCTC.